Okay, so today we're going to start chapter 4 of the PowerPoint lectures. There'll be a lot of slides in this chapter that we will skip, and I'll just use an X to signify that, as I just want to go through the important parts and highlight those in accordance with the video lectures that you've been watching. So in this chapter, it's split into a couple of different parts. Here we're going to look at reactions. When we look at a reaction, remember the reactants are always on the left side of the arrow, and the products are always on the right-hand side of the arrow. Okay? And when we study a reaction, remember we always look at it in a couple of different ways. One way is by thermodynamics, which is looking at energy changes that accompany the reaction. A second way is by way of kinetics, where we look at the reaction rates of the reaction. Does the reaction occur fast? Does it occur slow? In thermodynamics, is there an energy drop, or does the energy rise in the reaction? And so here we'll be talking about favorability of a reaction. Here we'll be talking about how fast or slow the reaction occurs. The mechanism, remember, is the step-by-step description of how a reaction happens. Okay? Or what I like to refer to is that it is the logic of the reaction. And the key thing that we use to show the logic of the reaction are these arrows that will designate electron movement. This chapter begins by looking at the chlorination of methane, and here we use heat or light to initiate this reaction. Remember, this reaction is a free radical reaction, and this is the overall reaction here, methane plus Cl2. One chlorine goes on there and the other chlorine attaches to a hydrogen. Okay, and again the need for heat or light, okay, in order to generate radicals. Okay, the most effective wavelength is blue, which is the high energy wavelength in terms of using light. Okay. So in the free radical reaction we have an initiation step, which is simply the production of radicals, and we then have a propagation step where the radical now reacts with the organic molecule to start producing the product. And lastly, we have the termination step, which are side reactions that interrupt the overall reaction, but the key thing here in the termination step is you start getting radicals combining, and so you start losing radicals, and so the reaction starts slowing down. In the initiation step, we take the weakest bond, which is that between chlorine or any two halogens, and a photon of light. Okay, so here we're using light as the energy source. Does a homolytic cleavage, and so each chlorine gets an electron, and these single electrons here are what are called radicals. The Lewis structure of radicals can be shown like this, or oftentimes we'll just simply write it as Cl dot. Okay, same thing for these other radicals, the hydroxy radical, and so on. Okay, so the radical we always show by a single dot on that atom. Radicals are reactive because they have an odd number of electrons, which is one short of the octet rule. Okay, halogens have 7 valence electrons, so one of them will be unpaired, a radical. we refer to halides as atoms, not radicals. Okay, no big deal here. Propagation step. Okay, so here we take Cl dot and we do a hydrogen abstraction. So it takes the hydrogen on the carbon and the other part of the bond, its electron stays with the carbon atom. And so we end up forming this methyl radical, and HCl, hydrogen chloride, forms as a byproduct. In the second step, okay, remember there's always two steps in the propagation step. In the second step, we take our radical that formed, this time the methyl radical, and we react with an unused Cl2. And so the radical takes one of the chlorines, and the other electron in this bond stays with the other chlorine. And so we get a Cl dot forming here. And so the overall reaction looks something like this: the first propagation step, and then the second propagation step. Okay, so the overall reaction is this here, and here we just broke it down mechanistically into its two individual propagation steps. Okay, so if you were to add these two propagation steps, the chlorine here and the Cl dot here would cancel. Okay, and the methyl radical here and on this side would cancel, and so we end up with this overall reaction once you subtract. Termination reactions, where we combine any two radicals, so a methyl and a Cl dot. Okay, remember we always produce a non-radical, so we are quenching the radicals because there's no radical on this side. Other termination reactions, you could have two Cl dots reacting, okay, or you could have two methyl radicals reacting, okay, or the thing could even react with the wall of the container and so form a bond to it. Okay, but these are the two main ones here that you want to be aware of. Okay, we can even look at equilibrium constants. Remember, the definition is the product concentration over the reactant concentration. So for our reaction, this is our overall reaction. So the equilibrium constant will be the products over the reactants. In this case, it turns out to be 10 to the 19th. Okay, this is measured. You weren't able to predict that. But that means, since it's a very high number, it's a very favorable reaction. Okay, so a large value indicates the reaction goes to completion. Can also look at it in terms of a free energy change. Okay, so remember the delta G is the energy of products minus the energy of reactants. Okay, so delta G is the amount of energy available to do work, often called the Gibbs free energy. Okay, reaction with a negative delta G is what we say is favorable or spontaneous. Okay, remember this delta G equation from general chemistry? Factors that determine delta G, you have the enthalpy factor and you have the entropy factor. And so here we have the Gibbs free energy equation. Delta G equals delta H minus T delta S. So here, talking about enthalpy in a little more detail. Remember, enthalpy is the heat that is either released or absorbed. Okay? If the heat is released, we say that it is exothermic, or that delta H will be negative. If heat is absorbed, we say that it is endothermic, and so our delta H will be positive. Okay, reactions favor products with the lowest enthalpy, because that's always giving the strongest bonds. When we talk about entropy, remember we're talking about randomness or disorder or lots of freedom of movement. Increasing heat, volume, or number of particles increases the entropy. Okay? So these three factors can govern entropy as well. Spontaneous reactions always maximize entropy and minimize enthalpy. Okay? So spontaneous reactions, or favorable ones, are where delta S is positive and delta H is negative. Okay, here's just some solved problems using calculations. We're not going to fool around with this stuff. Okay. Bond-dissociation energies. Okay, so this is the energy to do what? To do a homolytic cleavage. We'll often call these BDEs. Okay, so remember, a BDE is the energy to do a homolytic cleavage. And these BDEs can be used to estimate the delta H of a reaction. Okay, so a homolytic cleavage, when the bond breaks, each atom gets one electron. And a heterolytic cleavage, when the bond breaks, the most electronegative atom gets both electrons, and so it would get a negative charge, and the other atom would get a positive charge. Okay? So heterolytic cleavage always involves ions. Homolytic cleavage always involves what? Radicals. And here we see that. Here's some homolytic cleavages going on. And here with chlorine to get 2 Cl dots. Okay, note that takes a positive energy or enthalpy input. Okay, in a heterolytic cleavage, here we're saying that both of these electrons are going to B, and so B gains a negative charge, leaving A with a positive charge. And here we see that same kind of thing here. The most electronegative atom is chlorine, so these 2 electrons in this bond are going to the chlorine to therefore make it Cl minus, and leaving behind a positive charge on this carbon. You can then add the enthalpies up to get the overall enthalpy change. We're not going to fool around with this stuff here. Okay, kinetics. When we look at kinetics again, we're looking at the reaction rate. The rate of reaction is a measure of how the concentration of products increases while the concentration of starting materials decreases. Okay, a rate equation, or often called the rate law, is the relationship between the concentrations of the reactants and the observed reaction rate. Okay, so you might remember this from general chemistry. And remember, always the rate law is determined experimentally. You can never predict it. So in this case here we have a hypothetical reaction of A plus B going to C plus D. So the rate law will be the K, which is the rate constant, times the concentration of B times of A times the concentration of B. And then you have the exponents with both of these, which are called the order with respect to their particular concentrations. And remember, the addition or the sum of those exponents is what's called the overall order. So the order is the number of molecules of that reactant which is present in the rate determining step of the mechanism. Okay? So again, we're not going to get too heavily into this, as this was more general chemistry stuff. Same thing here when we talk about the activation energy, but let's discuss it because we'll be using it in this chapter. The activation energy is EA, and it's related to the rate constant in this particular manner. There's a temperature dependence of the activation energy. Okay, you can see the height of this hill. Okay, what we're doing is plotting the fraction of molecules with a particular energy versus the energy. You can see as we increase the temperature, what happens? The energy shifts to the right. Okay, in a lower temperature, the maximum is to the left. Okay, so at higher temperatures, more molecules have the required energy to react. Okay, so if the energy to react was, say, at 4 kilojoules per mole, note in this curve with the higher temperature, I have a higher number compared to this lower temperature here. Okay, so that's what these two curves are designating. So a higher temperature gives me more molecules with sufficient energy able to react. Here's a energy diagram of a exothermic reaction. So we always draw the reactants on the left-hand side of this curve and the products on the right-hand side, and there's a hill in between them. Okay? The height of this hill is what's called the activation energy, EA, and the distance between the reactant to the product is the delta H. Note that the delta H is decreasing, and so as a result it is negative, and a negative delta H is always exothermic. So this is an exothermic reaction, or what we can also say is a favorable reaction. Next, we can look at reaction diagrams for multi-step reactions. The highest points, again, are transition states. The lowest points are intermediates. The reaction step with the highest activation energy is the slowest step, and so we always call that the rate limiting or the rate determining step. So here is an example of a multi-step reaction. So here is the first step. Note, in the first step, I go up in energy, so this would be an endothermic step or an unfavorable step. Here is the second step, and note it is downhill or favorable, or delta H is negative. Note this activation energy is higher than this activation energy, and so as a result the first step is the rate determining step. Okay, here are some comparisons. If you look at the different halogens, okay, if we used fluorine, fluorine has the smallest activation energy, and as I go down the group, I get a larger activation energy. Note too that my rate at 27 degrees is highest for fluorine and then gets smaller as I go down. And if I increase it to 227 degrees, my rate goes higher, as I would expect. Okay? The reason for that is the temperature helps me to get over the hill of the activation energy. So what are some conclusions? Okay? With increasing activation energy, my rate decreases. Okay? Because I got a larger hill to get over. With increasing temperature, my rate increases. Okay? So you can always view that temperature as the gas pedal to get over this hill. So if I have more gas, or I'm pressing the pedal down a lot harder, it enables me to get over that hill a lot faster. Okay, fluorine is so quick that it reacts explosively. Chlorine at a more moderate rate. Bromine must have some heat to react, and iodine doesn't really react much at all. Okay. So here they just give you some variables and ask you to draw this reaction coordinate diagram. Okay, so here again the delta H is positive, so it's an uphill or unfavorable reaction. Okay, so here the chapter shifts a little bit. Okay, so we look at primary, secondary, and tertiary hydrogens. Remember, a primary hydrogen, okay, such as these, are attached to a primary carbon. Primary carbon is one that just has one other carbon on it. Secondary hydrogens are on a secondary carbon, and a secondary carbon has two carbons on it. And a tertiary carbon has three carbons on it, so the most it could ever have is one tertiary hydrogen. Okay, looking at the mechanism here for chlorine reacting with propane. Okay, note there are two different types of hydrogens. You have a primary here and secondary here. So the chlorine could attack a primary hydrogen to form a primary radical, or it could attack a secondary hydrogen to form a secondary radical. So in either case, if you had the primary radical, it could react with chlorine in the second step of the propagation and so form this primary chloride, or could react with the secondary radical to form this secondary chloride. Okay, here we're looking at the energies for these types of bond dissociations or homolytic cleavages. Okay, if you look here for CH4, to break one of its bonds takes 435. To break a primary carbon-hydrogen bond, look, the energy goes down. To break a secondary, to form a secondary radical, look at that, the energy goes down even more. And lastly, if I want to take off a tertiary hydrogen to give a tertiary radical, the energy goes down even more. So here what we find is the energy decreases as I have higher number of carbons on the radical. So I'm starting to see a radical stability order. and here they are. Tertiary radicals are more stable than secondary radicals, which are more stable than primary radicals, which are more stable than the methyl radical because it doesn't have any carbons on it at all. So carbon atoms on a radical help to stabilize the radical. Okay, and here you see it in sentence form. Okay, and here you can see it in a reaction coordinate diagram. Okay, so for the primary radical to form, it would be 13 kilojoules higher in energy than the secondary radical to form. So this radical here forms a lot easier than this primary radical. You also see the difference in the activation energy. The primary has 4 kilojoules higher activation energy than the secondary radical. Okay, so again, a lower activation energy means a faster rate, so that the more stable radical or intermediate is forming faster. Okay, we'll just skip this here. Calculations. Okay, skip this stuff here. Here what they do is do the same reaction, but this time with bromine. Okay, and if you do that, if you look, you get a large number of the secondary bromide compared to the primary bromide, and these numbers are more skewed than the chlorination case. Here's the energy diagram. Okay, we see that in order to form the radical, okay, it takes more energy for the primary than the secondary, but note the energy difference this time. It's higher compared to the chlorination case. Okay, and so this introduces us to what's called the Hammond Postulate, okay, which states that related species that are similar in energy are also similar in structure. And here it is. The structure of the transition state resembles the structure of the closest stable species. So if you have an endothermic reaction, the transition state resembles the product. If you have an exothermic reaction, the transition state resembles the reactant. Okay, so you want to remember that. This is the essence of conclusions of the Hammond Postulate. Okay, so make sure you have these down. Okay, so here's some energy diagrams to show this principle of the Hammond Postulate. So here, if I look at a endothermic reaction, the transition state, which is right here, is closer to this product than the reactant. Versus an exothermic reaction, the transition state is what? Closer to the reactant than the product. So it looks more like the reactant, and this one over here looks more like the product. Okay, so we see this even more. The endothermic is closer in structure to the product, and the exothermic is closer in structure to the reactants. We can also talk about what's called radical inhibitors. Okay, these are things often added to food to prevent spoilage by chain reactions. Without an inhibitor, each initiation step will cause a chain reaction, so many molecules will react. what an inhibitor does is it combines with free radicals to form a stable molecule. Examples are vitamin E and vitamin C. What they do is they can react with radicals to stabilize the radical so that it prevents it from doing further damage in our bodies. Okay, so these are the importance of taking antioxidants. Antioxidants like these two are able to quench radicals. Here are some diagrams of chain reactions. Okay, and if I add an inhibitor, what it does is it prevents the reaction from going on. So an inhibitor reacts, and once the inhibitor absorbs the radical, it's very stable and it's very stable in order to continue on with any other reactions. Here, switching gears to other types of intermediates, you can have a positive charge on a carbon. That's called a carbocation. Here's the radical. If I have a lone pair on carbon to give a negative charge on it, I have a carbanion. And here, when I take away a hydrogen and still have a lone pair, I have now a neutral species that we call a carbene. Carbocation structures, okay, they form on sp2 carbons, and the big thing that you'll want to remember is that they have an empty p orbital associated with them. The carbocation is also called the carbonium ion and also called the carbenium ion. Okay, so remember that it's sp2 hybridized with an empty p orbital. The stability of the carbocations is the same stability order as that of radicals. So the tertiary is the most stable, and as I go down this way, I get less stable. So again, the more highly substituted carbocations are the most stable. So stabilized by alkyl substituents in two ways. Okay, so you may wonder why putting more carbons on these makes it more stable. Well, one reason is what's called the inductive effect, where this is the donation of electron density through sigma bonds. And another reasoning is what's called hyperconjugation, where a sigma bond can overlap with the empty p orbital to help stabilize the p orbital. So here's an example of hyperconjugation, where you have a sigma bond weakly overlapping the p orbital to help stabilize it by giving some of its electron density to it. Okay, so here's resonance that we will again hold off until organic chemistry part 2. Okay, here's a picture of a radical. Okay, so this odd electron or the radical is in the p orbital. And again, the stability order of radicals right here. The stability of them is shown here again in greater detail. Okay, again, we won't deal with radicals just yet. The carbanions, okay, here I got this lone pair on the carbon giving the negative charge, kind of similar to ammonia. So carbanions are nucleophilic and basic. We'll see that especially when we get to what are called Grignard reagents. The stability order of carbanions is the exact opposite of carbocations and radicals. So the less substituted carbon is most stable, and the most substituted is least stable. Okay? So this order is the opposite of carbocations and radicals. Basicity, okay, so again that carbon can act as a base. Carbenes, what we have is an interesting structure. We have a empty p orbital on carbon, as well as a lone pair in an sp2 orbital. So carbenes are neutral. It has an empty p orbital, and so it can act as an electrophile. And it has a lone pair right here, so it can also act as a nucleophile. So very interesting properties with carbenes. You might ask, how would you form a carbene? Well, we could take OH minus with tribromomethane, form this, then a bromine can leave, and we get this dibromocarbene. Okay, we're not going to talk much about carbenes anymore, just want to get you introduced to what they are. So here's a summary of all the different reactive species that we've talked about. So a nice little table that you might want to jot down. And that's the end.